So this is a mixed event. It's a regular physics colloquium, but it's done within the workshop. 60 years, first 60 years of coherent optics, and we are celebrating the 80th birthday of Asher, sitting here, from Zato Asher. And the subtitle says featuring 3 generations of graduate students. We only have one colloquium lecture, so actually the entire plan of the workshop, this is a picture of Asher, and once the lectures in the morning, the speaker then showed that this is not a picture of Asher, this is an output of a laser resonator that lasers in an Asher mode. And this is real experimental data. So this is Asher, and this is the plan of the entire colloquium. And so some of you may know that Asher had many students, and many good students throughout his academic career. Many of them went to industry. Many of them stayed in academia. And actually, I just counted 11 of the Weizmann, which are belonging to Asher, children, grandchildren. So I leave to you to count and to see if you identify all these 11 names. So there was plenty of choice, and we needed some objective criteria because we only have one colloquium in order to choose Nirit. So we found 2 criteria. First, she's an excellent scientist, and she does very interesting research, and she's going to give an excellent talk, but there are others as well. So Asher has a big family, academic family, but it's also, like some other families, it's a complicated family. And for example, you could find these cross links. So Nirit did her PhD with Yaron, so she's a academic grandchildren of Asher, but she also did her master with Asher. So she's also the children of Asher. So because of all these reasons, we chose Nirit to give them.
But it's never the kids' fault for this kind of complication. It's the parents. Okay. Thank you very much, Nir, and Mazal Tov Asher. It's a great pleasure to be here at your birthday, so Mazal Tov. And I must say that when I joined Asher as a master's student, I think the most important thing I learned from him is that it's not only important to do excellent scientific work, but it's also very important to do it in a very nice, collaborative, and supportive atmosphere. And this idea, I think, it's the most important message that still influence our life every day and makes the AMO group at Weizmann so wonderful. So thank you very much for that. And another thing which I remember is that when I enter Asher Friesen lab, so of course the first thing they do is take us into the basement where we have all the nice, we used to have all the nice hologram. And I was really fascinated by this holography, by the concept of holography, because for me it was the most visual way to observe the wave properties of the light. So what I will try to tell you today is how we can take this concept of holography and then transfer it from the spatial domain into the time domain, into an extremely fast resolution in the time domain, and how we can take a holographic setup and then transfer it from a large macroscopic table that any student can learn how to align down to the scale of a single atom or a molecule. But before starting, let me first thank my wonderful group here at the Weizmann Institute who actually did the experiment which I will describe today. So special thanks to my former students, Dror Shafir, Oren Ras, and Ada Soifer, and many thanks to wonderful group of people, Barry Brunner, Doron Azuri, Michael Kruger, Oren Pedatzul, Gar Ornstein, Ayelet Uzan, Gidi Alon, and Shaked Rosen from my group. My group studies, as you can understand from the title, extremely fast phenomena in nature. And those fast phenomena are associated with very fast electron dynamics. And we try to do that by developing new tools, most advanced tools, for fast photography, ultra-fast photography. But this idea is not new. In fact, a very famous story takes us back to the year of 1872 to a very famous bet. I'm sure some of you are familiar with it. And the bet was on the following question: when I watch a horse as it runs, is there exists a moment in time in which all four hooves of the horse simultaneously leave the ground? And this question remained open for many, many years, several decades, until a famous photographer, Edward Nirit, developed a new technique, an extremely fast shutter, or fast at a time. And with this technique, he was able to capture the motion of the horse, and then by taking several snapshots, he was able to, in fact, introduce the first movie in history. And indeed, when we look at this movie, we realize that there is a moment where all four hooves of the horse leave the ground. By the way, he won a nice prize of $25,000 for this movie, which was quite impressive at the time. In my lab, we try to do very similar action. We face similar challenge. However, we do not look at large macroscopic objects. We try to look at much, much simpler systems, such as atoms that move inside molecules or electron that moves inside atoms. And that would take us over almost 12 or more orders of magnitude in the time domain. And if we start with molecular dynamics, we understand that most of the phenomena that we're familiar with, such as rotations, vibrations, chemical bond breaking or creation, they all evolve on a typical time scale of tens to thousands of femtosecond, and 1 femtosecond is 10 to the minus 15 of a second. And this time scale is so short that there is no electronic device fast enough to capture their motion. We cannot use electronic devices. Instead, we use a very unique laser source. And if you'll visit my lab, you will see this monster. It is composed of tens of mirrors and grating and prism and lenses. It's a nightmare to align it every morning, and my student can testify. But once it works, it provides us with a very unique outcome. It provides us with optical light, coherent light, which is not emitted continuously in time. It is emitted in short pulses. And the typical duration of those pulses is of the order of 10 femtosecond. And these pulses really serve as almost, as I will soon show, the fastest camera in nature. So with those pulses, we can capture the motions of atoms inside molecules, and we can really watch how very basic chemical phenomena evolve on their own natural timescale. But we can go further than that. We can ask the next question. So if we can capture atoms dynamic, can we go to electron dynamics? And that would take us 3 orders of magnitude to a shorter time scale known as the attosecond. So electron interacts, they correlate on a much, much faster time scale. And this time scale is between few tenths, hundreds, thousands of attosecond. And this time scale truly defines, I think, the main challenge, the current challenge in ultra-fast science. And let me just say, before showing several experiments, most of the phenomena in this regime have not been resolved yet. Most of them are well predicted by theory. We can predict what's going on when we pull an electron, when we look at different phenomena, but we have not been able yet to resolve them in the lab. And once we enter the attosecond regime, then we can ask ourselves several very basic questions, and I can give here only just a few examples. How long does it take to pull an electron from an atom or a molecule? Is it an instantaneous process, or are there any time delays that are associated with this mechanism? And as an experimentalist, I guess I should ask myself, can we measure those time delays? Can we follow the process of tunnel ionizations? And again, what are the time delays that are associated with this process? How are they linked to the different eigenstates of the system that play a role here? And we know that once we pull an electron, then in many systems, there will be a very fast rearrangement of the other electron. We create a whole wave packet. And this whole wave packet, in many cases, is not stationary. So it should evolve. And in many, many systems, it evolves extremely fast. Can we follow its evolution? And can I go, and this is really, I think, a major question in attosecond physics now, can I go from the measurement of very simple systems such as atoms and molecules into more complex systems such as biological molecule? and then, for example, watch how a charge migrates through a molecular system. If I can do that, then that will provide me a very accurate probe of the different electronic properties along a molecular chain. And there are many, many other questions. Now, the main challenge, of course, is the typical timescale. The laser that I'm working with in the lab, that most scientists work with, the ultrafast lasers, the most sophisticated system we can think of, emit the light in the visible or IA regime. So the typical period for the optical cycle is between 1 to few femtoseconds. My laser is in the 800 nanometer regime. The optical cycle is 2.6 femtosecond. So what we are trying to do here is very challenging. We're asking questions about phenomena that evolve during a fraction of an optical cycle. So really the challenge is, can we zoom into the optical cycle and watch how those phenomena evolve in time? And I can take one step forward and ask, can I see how the laser itself influences those phenomena? And this is a completely different regime compared to the one that we have learned in our undergraduate school. Usually the oscillating field is the fastest time scale that exists in a problem. Here, it's quite the opposite. And in many of the phenomena that we look at, the oscillation of the laser field would be the slower parameter that we change in our system. So the ability to look at those phenomena, to ask those questions, has become able due to one major important breakthrough in our field. And this breakthrough is the discovery of attosecond pulses. And this discovery was done in a laboratory in France, a small lab in France. Attosecond pulses, by the way, were discovered almost by mistake, by an experiment which was not well understood at the time. But once people have observed them, it led to a great excitement because it was clear that now we can enter a new regime, perform a completely new type of experiments. So here is a picture of my lab. This is the Munster laser system that you can see in the back. And just looking, I think this is Berry, but I'm not sure. I guess we were quite worried that this morning the laser didn't work again. And in this lab that is composed of many, many components, there is one crucial component. There is one crucial component here, and here is a zoom into this component, where we focus intense laser field into a tiny spot of only a few microns. And in this spot, we have extremely high intensity, about 10 to the 13 watt per centimeter square. So obviously, there is a highly nonlinear light-matter interaction that occurs here. And the light-matter interaction may lead to many, many phenomena. But the most important one that we focus in my lab is a phenomena at which coherent light is emitted by this interaction. This coherent light is in the XUV regime. And the unique property of the light is that it is composed of pulses having about 100 attosecond duration. Okay, so once people have realized that they can produce attosecond pulses, now we can forget about the complex interaction that led to their production. We can think of it as an almost black box. We have no idea how those pulses are generated. Let's take them in order to perform a measurement. And in the past decades, there have been a large number of many, many beautiful experiments that took those attosecond pulses and perform very fundamental experiment trying to answer some of the questions that I raised at the beginning of my talk. And here I chose only one example. There are many others. This is a very nice experiment that was performed at the Max Planck Institute. Here they superimpose an isolated attosecond pulse with a 2-cycle IR field. And by scanning the delay between the two, they were able to probe the instantaneous strength of the laser field. So here the attosecond pulse acts as a delta function. At each delay, it probes the local strength of the field. And now by scanning the delay, they were able to perform what they call the first direct measurement of the light wave. We can argue with that, but still I think it's a very well-known outcome in our field. So we can take those fastest camera that technology or nature provides us and perform the most accurate measurement. In my group, we chose a completely different direction, a completely different approach. We have decided that we can stop at this point and then take one very important step backwards. And by doing so, instead of using the pulses as extremely fast camera, we will focus on the interaction itself And as I will show, it can serve as an extremely accurate and very unique measurement. So how do we produce those attosecond pulses? It seems like a complex interaction. We are far from the perturbative regime that we have heard this morning. Many photons are involved. I don't know how to count the number of photons which are involved. But a well-known scientist in our field, Paul Corkum, who was also my postdoc supervisor, has been able to take this complex interaction and then describe it by very simple modeling, a model or a story that can be explained almost to any high school student. So within this picture, let's think of an electron which is bound to an atom or a molecule. And at the peak of the laser cycle here, the barrier is suppressed. I'm not sure how well you can see it with the screen. The barrier is suppressed and an electron can tunnel out. Once the electron is there, it feels a very strong oscillating laser field, is now accelerated by the laser field and then accelerated back, and with some very, very low probability, it may recollide with the parent ion. And recollision leads to the emission of coherent radiation. It's a very high nonlinear up frequency conversion with a very different mechanism compared to the one that we have been familiar with. And this radiation can be emitted in the XUV or even X-ray regime. And the unique property of this radiation is that it is emitted in attosecond duration, since the entire mechanism from ionization up to recollision evolved during less than one optical cycle. Therefore, the pulses will have sub-cycle duration or attosecond duration. And the frequency of those photons are dictated by two main components. It is dictated by the ionization potential, how difficult it was to ionize those electrons, and the kinetic energy that the electron accumulated in the continuum. So if I find way, and there are many laboratories that dedicate their research finding ways to increase this kinetic energy, then we can go from the XUV into the X-ray regime. And currently there are new and exciting results showing the possibility of really taking this tabletop experiment and then pushing it into the X-ray regime, where it really opens up a large range of new and exciting applications. But I will focus on the temporal property of this interaction. In fact, we repeat the story more than once. We have a multi-cycle laser field, and therefore at each half cycle, we pull an electron, we accelerate it, we lead to recollision, and therefore, instead of one attosecond pulse, we have a series of them. We have attosecond pulse train, where each pulse is separated by half of the laser period. And this periodic feature in time is transferred to be a periodic structure in the frequency domain. And this is quite a modest spectrum that we measure in the lab. Each frequency component is associated with an odd number of the fundamental frequency. Okay, we know that in order to generate even harmonic, we have heard this morning, we should break the symmetry of the interaction. And later on, I will describe how we can do that. But as long as the medium is symmetric and our field is symmetric, only odd harmonics will be generated. Here we can see up to the 39th harmonic. Of course, we can go much further. People have been able to measure the 1000th harmonic. And therefore, we call the spectrum the high harmonic generation. And this is the main observable in our lab. We can also think of this mechanism as a very accurate time-resolved measurement. Once the electron tunnels out in many systems, it leaves behind a whole wave function, a non-stationary state. And now this wave function evolved very, very quickly. It can change dramatically over less than one optical cycle. And then, as the electron recollides, it probes the evolved wave function, and the information is mapped into the high harmonic that we observe in the lab. And indeed, many people have used this idea in order to resolve fundamental electron dynamics or extremely fast nuclear dynamics. But when we think of this mechanism, in fact, we realize it's not that different from a hologram. So when I started my master, I learned how to build an hologram. I learned that I have to take an optical beam, split it into two. I have a reference beam. I put the object along the other beam. And here, on the hologram itself, I record the interference between the two. In our case, field-induced tunneling acts as a beam splitter. So it takes the electronic wave function and then pull a tiny portion of it out, but the two parts are coherent with each other. The free electron accelerated in the continuum. It accumulates high kinetic energy, but when it returns to the parent ion, it behaves almost, I'm not sure you can see this wiggling, as plane wave. It expands, and it expands at least from the point of view of the atom or the molecule, so it loses all its special feature. It's like illuminating the atom with plane wave, and recollision acts as a beam combiner. Once it recollides, it interferes with a bound state, and this interference induces a dipole moment that leads to the appearance of the harmonic that we measure. And when I learned about this concept when I was a postdoc, I was really fascinated, because I realized that what we have here is a unique combination of both temporal resolution with attosecond precision, but also extremely high spatial resolution. In fact, we do have here a typical resolution of about angstrom, which is the typical wavelength of the recolliding electron. So we have really a single particle interferometer, and this interferometer contains valuable information, extremely accurate information regarding the electronic wave function that we try to study. And the beauty of this mechanism, as in many other nonlinear processes, is that we can transfer the coherence of the laser through light-matter interaction into the coherence of the electronic wave function and back into the coherence of the new light that we generate. So although in my lab I don't have a single atom or a single molecule, I have a macroscopic ensemble of many, due to this coherence, all these electronic wave functions are locked to each other, they're all coherent, and therefore I can look at my many particle data, but still consider it as a single particle response. However, there is a major price to this picture. With a hologram, the situation is simple. We know we can take a hologram, we can illuminate it, and then reconstruct a 3D object. How do we do it in our case? How do I take the harmonic spectrum? I don't have any reference beam, right? Find a way to somehow illuminate it. We cannot illuminate it, so we have to find a way to analyze the data such that we reconstruct the dynamics under study. And this very simple and naive question, how do we take the data that contains all this rich information about the structure, about the temporal evolution of an electronic wave function, and extract the information? This simple question has been at the focus of the research in my group for several years. Okay, so what I will show today is how we can now take this very accurate interferometer and use it in order to observe fundamental phenomena in nature, where the most important question is, how do we tweak it? We know how to align an optical setup, but we don't know how to align this sub-cycle single particle interferometer. And in order to extract some information, we have to introduce new ways to align it, to tweak it, or to control it somehow. And the first subject of my talk will be dedicated into a study that has been at the focus of the research in my group for several years, the study of field-induced tunneling. Tunneling by itself is a well-known phenomenon. It describes the ability of a quantum wave function to penetrate. Here it is a static barrier. And we all know that the tunneling probability drops exponentially with the barrier thickness. We have a slightly more interesting dynamic to look at, because in the situation where I have described, the electron tunnels out, but the barrier is definitely not static. In fact, the barrier oscillates, it is suppressed, and then lifts up on a time scale of 1 optical cycle. So it oscillates very fast. However, we can still, and the very important work by Keldysh that was published at the 60s, have described the tunneling mechanism that occurs faster than even 1 optical cycle as almost follow adiabatically the modification of the tunneling barrier. So if we have this naive picture in mind, we understand that at the peak of the laser cycle, the barrier is suppressed, and here an electron can tunnel out with quite high probability, but few hundreds of attoseconds later, the barrier lifts up and tunneling probability drops to 0. So this is one of the fastest phenomena we can look at. It explains why it has been very challenging to follow the dynamics of tunneling. It evolved during about 200, 300 of attosecond. If I want to capture it, then I need a tool that will provide me about 10, 20 attosecond precision. And this is even shorter than the fastest attosecond optical pulse that has been that was ever produced. But field-induced tunneling is also a very important phenomenon because it is the starting point of all experiments that are performed in attosecond science. It is the starting point of many, many strong field phenomena. So first, maybe we should ask ourselves, okay, we have this dynamic, and definitely it's there in the spectrum. So when I measure the spectrum, the outcome of the tunneling dynamic are already there. But how do I map the dynamics into the optical frequencies that we measure? So we can think of an almost classical explanation to describe this mapping. So imagine the electron can, in principle, be released at different points along the optical cycle. But once it is released, I can forget about the tunneling mechanism, and I can use almost a classical prediction to describe how it will propagate and what would be the kinetic energy that it will accumulate. So, for example, if it is released late within the optical cycle, it returns after a very, very short time, but it accumulates very low kinetic energy, and this is energy as a function of time. And if it is ionized earlier, it will take him longer time and longer time to return. And the longer the trajectory, the higher will be the energy it exceeds. So there is a direct mapping here between, up to the cutoff, of course, there is a direct mapping between each trajectory length and an output frequency. And each optical frequency represents kind of one frame in our attosecond movie. But this is not enough. I've described an interferometer. So, of course, the basic question is, OK, how do we tweak it? How do we align it? And we need to do it very, very accurately. And we cannot do it after the light was emitted. We have to do it during the interaction time itself. And the only way to do that is to slightly change our laser field. The laser field is the main force behind everything that we measure. So we have to tweak it a little bit in order to manipulate our interferometer. I can take my strong laser field and slightly enhance it or suppress it, but this will be a disaster. Because it's a strong laser field, of course, it will change the interferometer, but it will not be the same interferometer. It's like you try to align a setup and you just smash your entire component. So you have to do it very, very precisely, and the only way to do that is by adding a perturbative field, a very weak field that will change 1 degree of freedom without changing all others. And the most simple way to do that is to add a weak field, orders of magnitude weaker than the fundamental field, which is polarized orthogonally to the laser field. And if I add this weak field, the main effect, it doesn't change the tunneling process, it doesn't change the acceleration in the continuum, it just adds a tiny, tiny drift to the electron, a lateral kick. But this kick can have a dramatic effect, because once the electron is kicked, recollision probability is suppressed and the emitted signal is suppressed as well. So this is a wonderful knob to turn. It's a knob that provides me with very, very high accuracy, few angstrom, yet I can resolve it in the signal that we measure in the lab. So this kick shifts the electron, shifting the electron suppresses the emitted signal. But what's important is that this is not a DC kick, it's an oscillating kick. And if it's an oscillating kick, it tells us that I can predict almost classically what would be the kick given I know the time of ionization and time of recollision.
The frequency of the second laser is higher than of the strong one?
Yes, it's double. It's a second harmonic field. Sorry if I forgot to mention that. And of course, it would be even nicer if I can have a very, very fast oscillating field. The faster the oscillation, the higher will be my temporal resolution. So this oscillating kick depends really on the moment the electron emerges into the continuum. Only once it's out, it starts to fill the drift, and the drift ends once the electron recollides. So schematically, we can think of different electron trajectories, which are born along different times, and each moment of ionization will experience a slightly different kick. I'm not sure if you can see that, but only narrow group of electrons are able to return to the parent ion and produce the maximal signal according to their moment of birth. And now if I change the two-color delay, I select a different group of electrons to return to the parent ion, And by doing so, I can really map each energy component with a very simple calculation back into their moment of ionization and moment of recollision. So what you can see here, the dots are the experimental reconstruction of ionization and recollision. The gray line represents our naive classical story. It's not that wrong. It does describe the basic mechanism. However, we see a clear deviation here, and the black line represents a more accurate quantum mechanical calculation that eventually tells us that the electron is not really born as the origin with zero initial kinetic energy. It is born slightly displaced with some initial velocity, and those tiny, tiny modifications, they're almost nothing, are observed in our measurement. And this measurement was very important because it mapped for the first time the very basic model that has been introduced by Paul Corkum 2 decades ago. And most importantly, it told us what is the typical timescale that we should expect the electron to tunnel out, and we see that this timescale is about 200th of attosecond. But this experiment didn't tell us anything about the barrier itself or the way the electron tunneled out. Why? Because it applies the kicking mechanism only after the electron left the barrier. So if we want to get any insight into the tunneling probability, how it changes during the optical cycle, obviously we have to apply our manipulation during tunneling itself. So again, we can enhance our field slightly, and by doing so, we will increase the probability or suppress it. But we can do it more accurately with the same tool, just rotated by 90 degrees. So we can put a very weak, and this is orders of magnitude, although I exaggerated here, than the fundamental field. And if the two fields superimposed, then the total field, the instantaneous field here, is enhanced, and the barrier will be slightly more suppressed. And when I shift the delay, then the two fields kind of partially cancel each other, and the barrier slightly lifts. So by doing so, I add a weak and time-dependent modification over the barrier itself. So what is the outcome of this? If you'll be in my lab and slightly tweak the laser intensity, there is no way to observe anything, because these are tiny, tiny modifications. We want to keep them tiny in order to keep the basic interaction unchanged, and it is buried in huge experimental noise and fluctuation. Well, as the electron experiences this perturbation, it accumulates a very small phase shift. In fact, it's a complex phase shift. We have an imaginary component to this phase shift that tells us by how much tunneling probability has been reduced or enhanced. And we have a real phase shift that was originated by an extra kick the electron experienced in the continuum. So the second harmonic field influenced the electron as it tunnels out, slightly enhance or suppress the probability, but then continues to work on the electron and slightly change its trajectory as it propagates in the continuum. And the total effect is a complex phase shift. And we all know, and we have learned that from Asher, if you want to measure a phase shift, then you need to use an interferometer. But we'll have to use a different interferometer. So if I want to measure a tiny event, I have to compare it with another tiny event. Luckily, we already have this in the time domain. So if this is our strong laser field, then we can think of two tunneling events that evolve at the peak and the deep of the optical cycle. The two of them are identical. If this is a single color field, and I can represent them with a two-arm interferometer, I have two identical events. Okay, here the barrier goes in this direction, here in the opposite direction, but the two are identical, and as a result, we observe odd-only harmonics. But once we now add a second harmonic field, we slightly suppress this barrier, slightly enhance the other one, we lead to an accumulation of a complex phase shift with opposite sign between the two arms, and the main outcome of this complex phase shift will be the appearance of even harmonics. So here we have broken the symmetry of the interferometer. Breaking the symmetry, we all know, leads to the appearance of even harmonic, and those even harmonics contain all the information that we need to know about the dynamics which is hidden here. And what we expect that as we change the two-color delay, we go from a situation where the interferometer is balanced and then unbalanced and then balanced again. So what should we observe in the lab? We should see clear oscillations of the even harmonics, right? And opposite oscillations of the odd harmonics. And they should be almost pi out of phase. Almost, but not exactly, because the phase is complex. And this is kind of a picture, a typical picture of what we observe in the lab. This is energy as a function of delay. And indeed, you see clear oscillations on both even and odd harmonics, and they are almost pi out of phase. Almost, but not exactly, due to the fact that this phase is imaginary. So I can take this raw data and then isolate the imaginary part of the story that tells me by how much I affected tunneling, and the real part of the story that tells me how much I influenced the classical propagation in the continuum. And this separation that you can see here, so we were very excited to observe that because this really isolates the barrier modification, the same barrier that influenced all our high harmonic experiment but was never isolated before. So now we can take this measurement and reconstruct by how much the probability, this is proportional to the tunneling probability, and here we see how it changes over time, and time here span over a temporal window of about 100 attosecond. So what we see here schematically is how much the barrier kind of changes, suppressed in time, over a tiny window of about 100 attosecond. Although it seems as if the barrier doesn't change much, the high nonlinearity of the process would tell us that the probability changes dramatically. So far I have described two experiments that shows that we can really take a complex measurement, and then by playing with the right knobs, we can isolate a certain degree of freedom, which we put at the focus of our study. And here we chose to focus on field-induced tunneling. We can focus on many, many other parameters. But after playing with this interferometer for several years, we have realized that this interferometer is very, very frustrating. You can think of the most accurate setup you can build in the lab, and let's assume that I can buy mirror mounts with accuracy of only few nanometers, okay? And I use those mounts for both the beam splitter and the beam combiner. But then I understand that I cannot really tweak them for a large dynamic range. The dynamic range of each mount would be about 1 micron. So I have a very accurate interferometer, but I really cannot play with that because eventually field-induced tunneling that serves as a beam splitter is fixed to be around here at the peak of the laser cycle. So if I want to ask how much the laser field influence, for example, the propagation of an electronic wave function, it's very difficult to answer this question because we cannot shift this beam splitter along the optical cycle. It's like taking one of the most important parameters and telling me, you cannot touch this one. Okay, and now the beam combiner is also quite limited. It is limited to be after one optical cycle. And if the phenomena evolves quickly but change over many, many femtoseconds, then my measurement ends after a very short time. And more than that, try to think that you have a beam splitter and a beam combiner, but once you touch the one, you also modify the other one. So the 2 degrees of freedom are both dictated by strong field interaction. There is no way I can influence tunneling without influencing the recollision. So all degrees of freedom are coupled, and therefore we were motivated to try and find a new way to somehow keep the accuracy and the uniqueness of the measurement, but increasing the dimensionality of our knob or of our setup. Okay, so, and one last thing. Tunnel ionization can pull an electron from the outer shell or few of the inner shell, and that will induce valence shell dynamics. But there is no way it can resolve core shell dynamics. Tunnel ionization just doesn't reach those energies because the tunneling probability drops so fast exponentially with the ionization potential. So we try to do experiment in the Attosecond regime, but there are many, many phenomena that we simply cannot approach with this mechanism. So far, I have described two main branches in attosecond science. One branch is the more conventional branch, takes the attosecond pulses and perform an accurate measurement. And the other branch takes the recollision as a self-probing scheme or as an internal measurement. And what I will describe here towards the end of my talk is a new measurement that we have developed in my group where we really integrate the two branches together. And what I will show is that how we can take an attosecond pulse and then inject it into another region where we produce attosecond pulses. In other words, what we have been studying for the past 2 years is how we can take attosecond pulses and then seed them into a new mechanism, a mechanism that was never studied before, and they serve as the starting point of attosecond pulse production. Okay, so let's take those pulses and now send them into a new interaction chamber. When those pulses meet an atom or an electron, they pull it into the continuum, and now we have an ionized electron. We can again send a strong laser field. In fact, it propagates together with the attosecond pulse. It's very difficult to throw it away. And this laser field may take the electron, accelerate it, and then lead to recollision. And we are familiar with this scenario. And once the electron recollide, again, it can emit optical pulses. But these are completely new optical pulses compared to the one that we started with. These are XUV photons at new frequencies that were not there before with attosecond duration. So here, attosecond pulses serve as the starting point for attosecond pulse production. And why is this mechanism so attractive? Well, now we took a very, very limited beam splitter, replaced it by photoionization, and we can scan the moment at which we release the electron in the continuum. We can decide whether we want to send it here, here, or here, and then watch how the oscillating laser field influence a measurement. But more importantly, we have completely decoupled the two main components of the story, the ionization and recollision, and that opens up a new type of measurements. We can do, instead of one-dimensional measurement, two-dimensional intertime domain measurements. And more importantly, photoionization can really take electrons from deeper and deeper level. The ionization truly depends on the frequencies that we send into our system. Okay, so here is an optical setup that was recently built by Doron Azuri and Michael Kruger. It's a quite sophisticated one. It's really taking attosecond experiments, I think, to their limit. So we first produced attosecond pulses here, and this is their discrete spectrum from xenon. And then we take them and inject them into a second cell where we superimpose them with a strong IR field. And here the new interaction occurs. So after many months of work, we were very excited to see the appearance of those new harmonics that were not there before. It was very difficult to detect them, but it was clear to us that this is not the end of the story, because the main question is, how do we describe the mechanism that leads to their generation? Is it just a simple multiphoton absorption? How can we find out whether this is really ionization followed by recollision or any other complex nonlinear interaction? Okay. What we did now, we took the ionization, the beam splitter, and shifted along the optical cycle. And by doing so, we see very strong oscillations of the signal. And clearly, there is one point. We have no idea what's going on there, but there is one point where the electron prefers to be ionized in order to recollide. One point that optimizes this entire mechanism. And this measurement corresponds to harmonic 25th, but if we go to lower and lower and lower harmonic, we see that this point shifts in time, and it shifts quite substantially over about 400ths of attosecond. So when we looked at those results, this is the optimal moment of ionization. We realize it spans over about a quarter of an optical cycle. And I think now it's a bit embarrassing to admit why we were stuck or puzzled by this measurement for such a long time, because when you take this figure and compare it to a story that was introduced 2 decades ago by Paul Kurkum, who didn't think at the time of this mechanism, it was a perfect match. In other words, the very, very simple classical high school story of an electron born at the origin with zero kinetic energy, accelerated and then recollide, agrees well with our experimental observation, or at least with the observation that maximizes the mechanism. But this is not enough. We wanted to have, I'm almost done, a deeper insight. So it's true, we can control the moment of ionization, but now we have higher degree of control. We can also control with a second harmonic field, and we learn how to do that, the acceleration in the continuum. We can now engineer the way the electron is accelerated once we have decided when to release it. So we can slightly enhance the trajectory, or we can slightly suppress this trajectory, and this is the second dimension of our experiment. So we have two dimensions, moment of ionization and trajectory length, and now we can fully control both of them with attosecond precision. And by doing so, we will accumulate a phase shift, but we know how to measure this phase shift. We can measure this phase shift by looking at the interference between two neighboring half cycles. So as before, we have two arms here. Each arm represents half an optical cycle. Without the second harmonic field, we have two identical events. But once we break the symmetry, now we modulate each trajectory, and this modulation maps into the signal of even harmonics that we observe in the lab. So this is the full 2D measurement. We control moment of ionization, and now we control the time of interaction in the continuum. And for each energy component, we map the full two-dimensional properties of the dynamics. And we can do that for the 18th harmonic, and I will choose one slice, 19, 20, 21, and look at this beautiful out-of-phase oscillations that tells us that indeed what we have been able to introduce here is an interferometer that goes from a balance, only odd harmonics, no even harmonics, unbalanced, only even harmonics, and then balanced again. So we take this new observation, which we had no idea what's the mechanism behind it, and we're able to show that indeed those electrons probably corresponds to recolliding electron trajectories, and their description follows a very, very simple, almost classical explanation. And we can see the pi phase shift between them, and we can also see a tiny slope that tells us that the trajectory becomes slightly longer and longer and longer, again, as could have been predicted 2 decades ago. Okay, so now, and this is just looking at the future, we can design different electronic wave functions that we want to learn, and then send them at the different points in time, let them propagate, and then probe them after hundreds, 200, or whatever, attosecond, and we can do it at each point along the optical cycle. Now, let me just mention one current experiment which is still under study. Doron and Michael are now trying to look at xenon atoms and initiate core shell excitation. We hope to be able to core shell excitation with this accurate interferometer. We see some signatures, but this is a story that I will probably tell in my next colloquium or next. Okay, so far I have described only atomic system. Towards the end of my talk, let me just mention that, of course, I think one of the major challenges is to go from this very simple toy model into the true and more realistic world where we have molecular system, but then the entire dynamics becomes more rich and more interesting. And what we have learned several years ago is that, for example, in CO2 molecules, we can take the electron not from one channel, but from several channels. So this is a very kind of interesting and exciting situation because we have at least 3 holograms to look at. We have the highest orbital or the 2 deeper one. They all interfere, but more than that, and this is something that we have learned only during the past year, we have an extremely fast population transfer between one orbital to another. So we pull an electron, and then during less than 1 optical cycle, the population translates between one orbital to another, and this coupling has never been measured before. We think that we see some traces of it, but it's still under study. And another interesting phenomena that we have looked at, so by doing so, we can really follow how the electronic wave function evolves in time. what we have also learned is that when we go to much larger molecular system as SF6, then the recolliding electron is not the same simple plane wave story that I've told you before. In fact, as the electron recollide, it can be trapped in several resonances in the continuum. So even in a very simple system like SF6, the electron is trapped in 4 possible different states before it recollides. And the recollision maps the interference between all those quantum path components. And that contains valuable spectroscopic information. We already saw some traces of this, but we have never been able to measure the dynamics. So let me just summarize. I hope I convinced you that Attosecond experiment enable us to take the concept of interferometer that any student learn how to manipulate and align, and then take it into the single particle regime. And by doing so, we can probe very fundamental processes. We have focused on field-induced tunneling. There is a large range of phenomena that have not been resolved yet. And really, I think most of the experiments have not been done, so we are developing the tool to resolve them. And we hope that with this multidimensional approach, learning how to control better and better the interaction, we'll be able to watch them. Thank you very much.
You mentioned that it would be interesting to look on really more complicated molecules. So how do you do that? How do you extend these schemes to multi-atom molecules?
So one way to extend the scheme, so I think we already did that. What we haven't applied our multidimensional approach, for example, to molecules like CO2 or SF6. What we are also trying to do is modify the fundamental wavelength of the light. And this is probably the most basic parameter to control. And by doing so, we can, again, decouple two different properties. But it's still a challenge. The major parameter to control is, of course, the molecular frame. So what we do is we learn how to align those molecules or excite them. So now I can do everything I told you about, but for example, looking at vibrating molecules. So I can ask, how does the barrier changes when the molecule vibrates? And one interesting phenomena that we saw is that the orbitals themselves sometimes switch. So this is just one example.
Can you do the recollision thing of the 800 with the Attosecond, with the UV, with the deep UV? Or is it weak in that? Too weak?
So it's
3 orders of magnitude below Atos. I mean, the signal frequency of the harmonics is very short.
So you mean the recollision itself? No. So first, this is a strong field interaction. So if you have a source for XUV radiation that provides me 10 to the 14, so but it's an interesting question. One idea that people had and we tried is to not induce the recollision but probe it with XUV. And if you probe it, then you can do all the games that we did so far, but with 2 orders of magnitude higher accuracy.
Probably with XUV, you don't need a strong field because of your single photon ionization, right?
This is also correct. Yeah, but then probably you pull all the electron, as we did in the last experiment.
Does the magnetic field of the electromagnetic wave play an interesting role?
Okay, this is an excellent question. In fact, we try to think of this direction. The magnetic field, if you take your field intensity and increase it by 2 orders of magnitude compared to what I currently have in the lab, then you approach some relativistic regime where you have the V cross B starting to influence your measurement. And then instead of doing something like this, it will push you away. So it kills recollision. But what we hope to see is that it doesn't kill recollision. It's still there, but it influences the dynamics. So maybe with stronger laser, if I'll be able to buy one, we could measure this. Who should I look at? Israel.
If you start not with infrared laser, but with X-ray laser, is it possible to get even shorter pulses with interaction with material?
The answer is yes. So if I'm able, so we already did that. If I take XUV and inject them, then that enables me to control some part of the interaction. If I can do it with X-ray, that it has the potential of giving me even higher accuracy. So the answer is, sorry?
Nobody tried yet.
Not as far as I know. And the problem is of course, the available sources. Yeah. Because you want it also to be coherent with the fundamental field.
Last question. I realize that it's difficult experimentally, but if you could have two XUV pulses as a control delay between them, would that give you different information? Would that be as opposed to XUV plus?
Definitely, yeah. Because if I have two XUV and I can control them, then I can do kind of a pump. Then I have really multidimensional spectroscopy experiment. So this is, you're describing really the dream experiment of taking, it's very similar to the multidimensional measurements that people do in the IR. But if we can do that with attosecond pulses, and not only control the delay between them, which is quite possible, but actually to see some observable measurement, then that will take the entire concept of 2D measurements in the IR and into the attosecond regime.